A quiet breakthrough emerges from a wonder crystal where electrons and their mirror holes collide under a storm of magnetic field. In this magical material, telluride-like atoms form a maze that is exquisitely sensitive to external conditions. Conventional excitons pair electron and hole with the same spin, a simple duet in the quantum dance. But under an ultra-high magnetic field, opposite spins lock together to form a rare spin-triplet exciton. The material in focus is a topological crystal where the internal maze shapes how electrons flow. In a near absolute zero chamber, a powerful magnet orchestrates the motion of electrons along a single path. As the field grows, the two key energy bands carrying electrons and holes converge into a one-dimensional, Euler-like mode. Researchers observe that the insulator awakens when a critical magnetic field flips the balance of charges. Charge neutrality does not come from vanished electrons, but from bound electron-hole pairs locked in place. The energy gap measured is about 250 microelectron volts, the precise cradle for the spin-triplet pair. Unlike common excitons, the spin-triplet form preserves the crystal's translational symmetry. The triplet state also promises better stability and strong magnetic fields. And crucially, it can transport spin without carrying electrical charge, potentially reducing heat. This discovery opens new horizons for low-power spintronics and perhaps quantum computing elements. The material studied is a topological compound whose internal maze is exquisitely sensitive to its surroundings. At extreme conditions, electronic doors tighten so much that motion becomes almost channeled along the field. The researchers used ultra-low temperatures and magnetic fields to coax the state into existence. As spins cross and align, the system reportedly switches from metallic to insulating, a dramatic phase change. Yet the Hall signal vanishes at criticality, revealing a perfect balanced neutrality. Calculation and simulation corroborate the experimental findings, reinforcing the 250 MeV gap. So why triplet? Because the opposite spins create a bound pair that preserves symmetry and transmits spin. The triplet state demonstrates compatibility with strong magnetic fields and potential for robust devices. In practice, spin currents could convey information with minimal heat production, a dream for chips. Researchers are already thinning the material to tens of nanometers to explore device integration. Gate-tunable devices could probe the exciton insulating states even further, at the two-dimensional limit. If zero magnetic field realization is confirmed, the impact would be even more profound. The researchers acknowledge this is a foundational experimental step with broader future applications. The current focus is on device fabrication that preserves two-dimensional quantum transport phenomena. The team aims to condense these insights into practical, low-power, spin-based computing elements. This breakthrough could have ripple effects across quantum information and neuromorphic technologies. The study in question shares its foundations in a 2020s-era topological material research narrative. Ultimately, the quest is to create computers that compute with spin, not heat, and dream of a cooler future.